this is Green's second identity, and homework number 2 just wants you to integrate both sides of the equation and apply the identity. So try it out. It shouldn't take you that long. It's not like the first problems that we did. But the next set of problems, I'm going to show you the derivation of the one-dimensional heat equation. And then we're going to go to Laplace's equation. I just want to hit every one of those equations like he has the math physics equations and derive them or show you where they come from. And we're actually going to get in dirty with the Laplace equation and solve it. So this is, there's more intuition than the book, but my thing is following Chris Tisdale's lecture rather than the book. The book is looking at, I think they're also looking at the one-dimensional heat equation, or maybe two-dimensional. So let's just start with the one-dimensional. And in a one-dimensional idea, it's just only a number line. That's the spatial component. You don't have a geographical area or a sheet of metal. That's why it's sometimes easier to think of a sheet of metal than it is to think of just one dimension. But think of a rod, and the direction on that rod is to the right, and you have a number line going through it that tells you where you are on that rod. X equals 0 is the left end of the rod. X equals L is the end of the rod. So there's some assumptions in the heat equation. The first is that that rod is made of uniform material, so that you don't have, it has toxins in it somewhere. And you also want to assume that the bar is perfectly insulated around it, so you don't have heat going through the bar. Like, you can think of one of those pizza style sleeves that your pizza comes in, so something's wrapped around it so heat is not coming out and through the rod. And you also want to assume that the bar is really thin, so the temperature might not vary much on a cross section. So if you take a little slice of it out, the temperature is uniform on that little slice. So there's a little slice up there. If we define U of x and t to be the temperature of the rod at time t position x, then the heat equation is written in this form. UT equals, I usually use a D, Chris Tisdale used an alpha, alpha squared. That number, I use the D because I think of it as a diffusion constant, but Chris Tisdale broke it down into its pieces where you have the constants actually mean something. These constants depend on the material, as you would expect it to, even if you think of it as a diffusion constant. How temperature is going to diffuse through that rod depends on the material of the rod. If it was copper, you'd expect it to be really diffusing through fast, if it was heat going through. And if it was wood, maybe not, right? So it'd be something different. Just like anything in calculus, we start at a derivation with taking a thin slice of something. So take a thin slice of that rod, let it go from x0 to x1 to represent that we have a slice of that rod. And then we're going to calculate the total heat inside that rod. So the total heat at time t is represented by an integral. And that integral comes from physics. It's the specific heat of the material, rho is the density of the material, and U of xt is temperature. So if you remember back to physics classes, which most mathematicians don't like, but if you remember back, you remember that temperature and density, and they're all related to each other. And this comes straight from that. So the rate of heat exchange with respect to time, the rate of heat change with respect to time, is calculated by taking a derivative. Now, pulling that, you're really taking the derivative on the outside of the integral, and then you're pulling that derivative inside the integral. So you're pulling a limit from the outside of the integral to the inside of the integral. If you had real analysis, you spend a lot of time talking about when you can do that. So this is engineering math. We just do it. It just goes in. So I don't know if you guys remember the Lebesgue-dominated convergence theorem. Did you guys learn that? And they talk a lot about when you can take a limit from the outside to the inside. So it's not.
I remember Dr. Trubat doing that with one of his proofs.
Okay, so it's an important thing. And then I'm going to write it this way. So far, so good? So where does the heat equation come from? What you have right now is the left side of the heat equation inside the integral. What you're going to do is find a second expression for the change in heat with respect to time in integral form and set the two integrands equal. And those two integrands turn out to be the left and right side of the heat equation. So here's the second part. The only way heat can flow in and out of the rod is through the ends x0 or x equals x, because we took that slice out. This is Fourier's law of heat flow, which is really the divergence theorem. And the reason these flows are, this is the rate heat enters, this is the rate heat leaves, and the Fourier's law is that this flow rate is proportional to the derivative with respect to x. So why are both of these terms negative? It's because we're making an assumption that there's a positive flow of heat from left to right. So then the first derivative with respect to space is going to be negative. And K has a name, it's called thermal conductivity, and brings back horrifying memories of physics. You remember these kind of things from physics, right? We're actually, math and physics are in the same department here. Aren't you guys working with, yeah. It's a sin, right? Huh? It's a sin to say these things, but most mathematicians don't really appreciate their physics classes. So what we have right now is that the rate of heat with respect to change in heat with respect to time is given by this expression. And we can take that expression and go backwards from the fundamental theorem of calculus. So we can think of this as a f of b minus f of a, and replace it, like go backwards and think of it as a integral. You know, thinking if you take this and integrate it with respect to x, you're back, and then evaluate at the endpoints, you're back over here. So you're really applying the fundamental theorem of calculus, which is kind of neat. So we have now two expressions for dH dt. We have the expression where we have this thing in the integrand with a double derivative of u with respect to x, and we also have a rate of heat change with respect to time from earlier written down this way. Set the integrands equal, and what do you get? You get the heat equation. So the book also, I just set the insides equal. Alpha squared was the constant, so I'll put on one side. So the book doesn't use Fourier's law, so go through it. It's just the divergence theorem, and then you'll see the connection between Fourier's law and the divergence theorem. They're really just using the analytical method, everything drops out, and you're left with exactly Fourier's law. So it's the why of Fourier's law using the divergence theorem. It's really cool. I think your book might talk about scaling up parameters, but maybe not. So in applied math, we always like to scale out the parameters. They're in there somewhere in time, but we scale them out so we can not carry around these parameters. We call it non-dimensional analysis or dimensional analysis. We're taking out these numbers. So the way you do that is you introduce a new time parameter as alpha squared times t. Then the derivative of u with respect to t bar is really alpha squared times the derivative of u with respect to, the derivative of u with respect to t is really the derivative of u with respect to t bar times alpha squared. If you replace that on the left side of the heat equation, you get the left side is the derivative of u with respect to t bar alpha squared, but on the right side there's no function of t on the right side that you're taking the derivative of, so you still have alpha squared uxx. And so then the alpha squares pop out of both sides, and you have just ut is equal to uxx. And then, of course, in grand math style, you just drop the t bar and you're left with t to confuse everybody. Where did the t bar go? And you have the non-dimensional heat equation. You don't have any scaling, you don't have any parameters.